Hello, welcome back. All right, so today we're going to do some non-conservative work examples. We're going to start with level 1 and we're going to work our way up from there. You can check that out on the next video. All right, so what are we going to do with this kind of stuff? Well, remember, non-conservative work has to do with the total energy changing. We kind of saw this equation in class, and we're going to use this same one each and every time here. It's just as we work our way up through the levels, we're going to use it in different ways, and we're going to see how this equation can change a little bit and how we can put different numbers into it. So this is the basic equation. The work of non-conservative forces is going to cause a change in total mechanical energy. We expanded this a little bit more in class so that we could say that the work of the non-conservative forces is going to cause a change in total energy, which would be the change in kinetic plus the change in gravitational potential energy. And that works if we are given energies in a problem, but in our first example here, we actually are not given our energies. We are given some other pieces of information though. So in this first example, we're going to talk about work done being done by some non-conservative forces that are pretty common, like friction and air resistance. So in this case, we have a 500 kilogram roller coaster coming over the top of a 20-meter tall hill with a speed of 3 meters per second. When it reaches the bottom of the hill, its speed is 15 meters per second. What is the work done by the forces of friction and air resistance? Now, in the last section, when we were talking about conservation of energy, the total mechanical energy would have been the same at the top of the coaster to the bottom of the coaster. But that's not the case here. Because friction and air resistance are doing work, they are going to change the total energy. So since friction and air resistance are doing non-conservative work, they're going to cause a change in the total mechanical energy. In this case specifically, friction and air resistance are going to take energy away. So we should have negative work being done when we actually go ahead and calculate this. But based on what we're given, we're not given kinetic energies and we're not given gravitational potential energies. We're given velocities and we're given heights. So we're going to want to take this equation one step further down and expand it a little bit further so that we are using velocities and heights. All right. So based on my givens, I have some heights, I have some speeds, um, I also have my mass. This is the equation I want to use. It has all my givens and my unknowns. Let's picture this equation, or picture this problem for a minute. All right, we have a roller coaster. It's up at the top here. It's starting with this initial height of 20 meters. All right, and it has a velocity up here, or a speed up here of 3 meters per second. And it's going to come down this, and gravity is going to do some work, and friction and air resistance are also going to do some work. And see, so that's the thing. We actually have many forces doing work here. We have gravity doing some work, but then we also have these non-conservative forces of friction and air resistance doing work. All right? And friction and air resistance, depending on where I look at this thing, this is a pretty steep coaster, right? Friction and air resistance are doing work, and they're always doing work in the opposite direction of what we're moving. So as we kind of roll down this hill, all right, friction and air resistance are working against us. They're taking energy away from our cart. So when it reaches the bottom, the velocity that we have here at the bottom, that final velocity, is going to be less than what it would have been if we didn't have friction. All right. So if we got down here to the bottom and friction didn't do any work, this thing would be going faster than if we did have friction. And that makes sense, right? So we want to know what is the work that's being done by these things if it reaches a speed of 15 meters per second when it gets down here to the bottom, which we'll call 0 meters. All right. And so we have all of our heights and we have all of our velocities, initial and final, and that's going to give us enough information to go ahead and solve for our work of our non-conservative force. So let's go ahead and we'll substitute all these values in here. The work of the non-conservative force, 1/2 times our mass of 500 kilograms. Final velocity is 15 meters per second. We're going to square that. We're going to subtract our initial velocity, which is 3 meters per second. We're going to square that. Plus, all right, so we ended those parentheses and we do plus. We have our mass here again, 500 kilograms, 9.8 meters per second squared. All right, Just to remind everybody, we use a positive 9.8 here. This is energy, so we don't use direction, all right? And then we're going to multiply that, I kind of ran out of room here, by our final height, which is 0 meters, minus our initial height, which is 20 meters, all right? So at this point, basically, we are just following the order of operations on the right side of this equation. So take a moment right now. You can pause the video, all right, and work that out yourself. All right. All right, through the magic of television here, I worked this problem out. And you're going to notice a few things that I just want to point out real quickly. So the first thing was don't forget to square your velocities, all right, before you subtract them. You can't subtract then square. That doesn't give you the correct answer. So we should get a 216 whenever we do that. And then over here, I have a 0 minus 20. That should give me a negative 20 here. So we don't want to watch that because positives and negatives are going to make a big difference here. So after I combine all of my terms here and simplify, I get these values. Notice that's a negative value. All right. And then I get the work of my non-conservative forces to be a negative 44,000 joules, or if we wanted to write that as a negative 44 kilojoules, we could absolutely do that. And so why is it negative? Well, namely because friction and air resistance, they are taking energy away from our roller coaster, all right? So as it falls, it's losing energy, all right? It's losing energy. So that's our first example. Let's move on to our next example. Okay, example number 2 here. All right, let's push a cart up a ramp and no friction, all right? So let's say we have a person, they're pushing a cart, and it has wheels, so it doesn't have any friction involved. They're pushing it up a ramp at a constant velocity that leads to the back of a truck that's 1.2 meters above ground level. How much work does this person do? All right, so let's draw this picture out for a moment. We have our ramp, all right? So we have a nice right triangle here. That could be useful in later levels maybe, right? And we know that when it reaches this height up here, which is going to be our final height, we're going to have reached a height of 1.2 meters. And if we start our box or our cart down here at the bottom of our ramp, then it's going to have an initial height of 0 meters. All right, so when we move this thing up, we're literally moving it up. What's interesting here, though, is when we start to think about velocity, all right? So we should always be thinking about what's our velocity at our starting point, what's our height at our starting point, what's our velocity at our ending point, what's our height at the ending point. We know our heights here, but what about our velocities? We don't know. We don't have a number, but here's what we do know. It is a constant velocity. So whatever the initial velocity is, the final velocity is the same value. It doesn't matter what we would pick, because in the end, in the equation, these things are going to end up canceling each other out. Well, let's see how that happens here. So we're going to go back to our original equation, all right, the work of the non-conservative forces. In this case, the force that's the non-conservative force is the man's pushing force. And as he pushes up the ramp, he's doing work on this cart, all right? And that's causing this cart to change its gravitational potential energy. But one thing that it's absolutely not doing is because it has the same initial velocity and final velocity, it's not changing its kinetic energy. So if I look at the way that I was writing this equation before, right, the work of the non-conservative forces is the change in total mechanical energy, and that would be the change in kinetic energy plus the change in gravitational potential energy, right? Because we're traveling at a constant velocity, there's no change in kinetic energy. Whatever it is, it's not changing. So the work that's being done isn't doing anything to change the velocity, it's doing everything to change the gravitational potential energy, okay? We can also see this in the next equation if I were to write it out one step further, right? 1/2 m times v final squared minus v initial squared plus mg h final minus h initial, right? Well, look at this equation. If the final velocity is the same as the initial velocity, and I square each of them and then subtract, then guess what? this is just going to be 0 in here, and 0 times m is 0 times 1/2 is 0, and so this whole term goes away. And so in this example, we don't need to think about kinetic energy at all because it's not changing. So the work of the non-conservative force is really just the change in gravitational potential energy. That's mg h final minus h initial. So we have to watch that. Sometimes if something doesn't change its height, then there's no change in gravitational potential energy. If something doesn't change its speed, there's no change in kinetic energy. And the work that's being done is just changing whatever's left over. So this kind of simplifies our equation a little bit. We can go ahead and plug our numbers in. All right, we know the work of the non-conservative force. That's going to be the mass of our cart, which I seem to have left out here. Let's say we have a 50 kilogram cart. All right, 50 kilograms, 9.8 meters per second squared. Again, remember positive, right? Final height, 1.2 meters. Initial height, minus our initial height, which is 0 meters. All right, this time it's positive. We have 1.2 minus 0, so that's going to be a positive value. Let you go ahead and plug that in. And we get to the work of the non-conservative force. That's the man's pushing force. All right, this person's pushing force is going to be 588 joules. And this one's positive. So why is it positive? Well, the cart has more gravitational potential energy than when it started. Where did that energy come from? That came from the man's pushing force doing the work. It did 588 joules worth of work to change that thing's gravitational potential energy. All right, those are level 1 examples. Give those problems a try and then move on to level 2.